Okay, then let me share my screen.
I'm already sharing.
You already share my screen. Okay, so can you see my screen? Please, can you guys see my screen?
Yes, we can see your screen.
Okay, sure. So let's start. We are starting with the chapter 4, after which we'll go and finish the chapter 3 we started earlier. Yeah, let me check if I'm recording. Please, if you have friends who are interested and they are still not here, please, because ask every question you have to ask today. Otherwise, if you send me a DM, I won't reply. Thank you. Okay, so we are starting with the SR drive, the switch reluctance drive. For those of you who did those of you who did a simple is it simple or special machines, okay, special machines, this is not the first time seeing anything like reluctance, okay, motors that use the reluctance principle. So in our special machines, we have the reluctance motors that uses just a reluctance principle, that flux will always use the path of what least reluctance. Okay, so if flux just like current, current will always choose a path with what the least resistance. So flux will always choose a path with what the least reluctance. So yeah, so that's the principle that the reluctance motors. But the ones we saw in special machines, mostly they use that for starting. Okay, so for the special machine, most of these machines they are single phase machines, and as at this point, we all know that single phase induction motors cannot start on their own. Okay, because they only produce what an alternating flux, so you don't have what a resultant rotating flux to cause what a torque to be induced in order for the rotor to what move. Okay, so then there's a need to split that single phase flux you have into two. That means you want to create two fluxes with what an angle between them. Then these two fluxes can interact to produce what a rotating magnetic what field. Yes. So we are looking at switch reluctance motors. This chapter is very short, and it's I thought about doing it first because since the questions are going to be like the optional part, you have 4 questions to choose two from each chapter. I think the chapter 4 is quite easier than the other chapters. So if you are able to master this and you master another one to it or another two, at least you have two that you can answer with what a backup. Yeah, so that's the plan. Okay, so I think the first two slides are English, you can read. So yeah. Okay, so just like the name implies, switch reluctance drives, they work on the principle of a magnetic what attraction. Okay, or it works on the principle that flux will always use what the path with the least reluctance. So this is how the motor works. If the motor rotor, right now we all know what rotor is, we all know what stator is. So if the rotor is such that the magnetic path has what a high reluctance, the motor produces a torque in order to align the rotor in the direction that the reluctance or the air gap between the stator and the rotor will be what small. Is that okay? So that's basically the principle. Then it's this motor does not have windings on the rotor. It only have what windings on the stator. So just the windings on the stator that produce what the working field, but there are no what windings on the rotor. Very important. So it uses what a winding which only requires switch DC instead of what AC. So it uses what fewer power electronic device switches. Maybe you see some diagrams, get this to the end of the chapter and you see that. And I already said that the rotor does not have what a current flowing through it because it has no what current what windings on it. Okay, then if that's the case, that because you don't have current carrying windings on the rotor that will have current flowing through them, which will produce heat, there is what? there is no cooling requirement for what the rotor. You only need what cooling requirement for the stator, because the stators have what windings that carry what current. So then they heat as time goes on, but the rotors do not what heat because they have no windings on them. Then there are no connections required to what the rotor, because if you are connecting, what are you connecting to? There are no windings on the rotor, so you don't need any connection. Okay, please, if you have any question, unmute yourself and ask. Sure. Okay, so now we are starting. So if current to flow, there must be magnetomotive force. In the last session, I explained what magnetomotive force means. Okay, that's the work done per unit or charge in moving that charge from what one point to the other. Okay, so I think you watch the videos. So I was saying that if you have a point here, Charlie, if you have a point here and you have a point here and you have an electron over here, you need to move this electron to here from this point to this point. Remember, there are atoms or positive ions, there are atoms in what the conductor. So as the electron is moving, there are other electrons that may try to what repel this electron. Okay, give me a second. Hello. Yeah, you are done. Should I take? You said, yeah. I'm not sure I can come to take junction right now. So I don't know. I'm at the College of Engineering. No, no, no. Unless shuttle or a boat. Okay. Okay. I'm in a meeting right now. Like I can't leave. Mhm. Okay. Yeah. Where you are going, that's not campus proper. Where you were going, that wasn't campus proper. If I knew earlier, I would have planned in that route. Yeah. Yeah. Mm. Okay. Then save them. Right. Okay. So let's continue. Okay, so yeah, so a certain amount of work needs to be done in order to move this charge from this place to this place. Okay, so that work done in moving this electron from this point to this point is what we call the magnetomotive force. Is that okay? And that because you are working, if you are working, is because there's some form of what uh, resistance over here. There's something that's preventing these electrons from moving to this point. Okay, so that resistance that the electron face from moving from this point to this point is what we call the resistance of the medium. Okay, so the same way, if flux has to move from this point to this point, it's going to have what some form of resistance in magnetic circuits. The resistance the flux is going to face is what we call the reluctance, represented with what a s. Is that okay? So then if flux has to move from this point to this point, then some amount of work needs to be done, or a certain force needs to be or exerted. And that force is called the magnetomotive force. Is that okay? This magnetomotive force is giving us, okay, let me go to. So the magnetomotive force, MMF is giving us the number of turns, okay, times the current flowing through the winding, and it's also giving us what the flux flowing times what the reluctance. So just like EMF is equal to current times what resistance. So this is the Ohm's law in magnetic circuits. I hope this makes sense. Okay, now let's look at something. Yeah, so in a magnetic circuit made up of ion and air gap, the reluctance is almost entirely due to what? Air gap. So this is what it's saying. Okay, so flux needs to move, right? The flux needs to move and maybe interact with this rotor or something. The reluctance the flux is going to face will be what? The reluctance in the air gap. That's what that point is saying. So look at the two positions over here. Look at the distance from this stator to the rotor surface at here. Look at the length of the air gap and look at the length of the air gap. It's very obvious that what the length here is bigger than what the length here. Okay, so if you take this, if you put these two scenarios in front of Flash right now, Flash will tell you that okay, most of them, okay, just like every human being, there are some human beings that if you tell her if you do this, you get it. That's what they will do. Okay, there are some Flash like that. Even though if there is high reluctance there, some of them will still what pass there. So it's not just human beings. They are also like that. But the idea is that most of the flags we use for the part with the least what reluctance. So just like we have this large air gap over here and we have a small one here, most of the flags will prefer what to have this scenario than this scenario because this will make what they need. You need a smaller or magnetomotive force. Okay, so the last video we recorded, I gave a certain a history about how the rotor evolved. I don't want to talk about that today. I'm not in the mood to say stories. Yes, so let's go. So what we are saying that if it happens that the rotor is in this position, okay, the motor is going to produce a torque that will cause the rotor to what? Move in this direction, to move into a direction like this, to have what? The least reluctance. Remember, this is just showing what? A two-pole motor. Is that okay? So it's just this. It can happen that there is what? Another pole over here. So another pole over here like this. Remember, the number of poles are always what? An even number, the total number of poles. Okay, then that this for a four pole, there may be another pole here, like this. This will be what? A three pole. Okay, so that means if it happens to be around this place or maybe closer to this one, this is going to attract it to come into the position of least what? Reluctance. Then once it moves to that place, another one is also saying that oh, it's so close to me. Okay, then a torque needs to be produced so that it moves this way. Then at the end of the day, you see that the rotor will be what? Rotating. Okay, so if a part of the magnetic circuit is movable, that if an mmf is applied, it always moves toward a minimum reluctance position. Enough of the English. Okay, so let's talk about this slide. Okay, so let's assume this is a north pole and this is a south pole. From physics, we know that what if you take a magnetic circuit or you take a magnet, its magnetic field strength is what is greatest at the center of what the pole. This we all know. Okay, so we are taking this line over here, which passes through what? This line over here, which passes through the center of what? Uh, the center of the magnetic poles. Then this is the rotor. So this is the rotor axis. This is the stator pole axis. So you can see there is a certain angle between the rotor axis and the rotor axis and the stator pole axis. This angle is what is called the rotor angle. So from this slide going on, we are going to be writing inductance as a function of what position. It is this position we are talking about. In this case, since the stator pole axis, okay, it's always going to be like this. It's not going to change because the stator is what is not is stationary. It doesn't move. Okay, so it's always going to be like this. We are using this axis as what the reference. So anytime we are saying we are talking about rotor angle, we are saying what is the angle of displacement, um or yeah, the angle of displacement between the rotor axis and what the stator axis. Please, any question? No question. Okay, so what's the angle of displacement? So every angle we are going to measure is going to be what? The angle of what? The rotor in reference to what? The stator pole. The stator pole axis. Please, is it clear? C'est clair? Oui. Let's go. Okay, this is the part I like. So let's go here. Okay, so from applied electricity, we were told that the voltage across an inductor is given as the inductance of the inductor times the change in current with respect to time. Okay, this is true, but it is partially true. It is true and partially true because all the inductors we've been looking at so far have what? Fixed what? Inductance. So then if the inductance is fixed, this here is valid. Is that okay? Actually, the actual equation is that the voltage across an inductor is equal to what? The change in the flux linkage. The flux linkage with respect to what? Time. Then the question is, what is flux linkage? Flux linkage is given as what? The inductance of the inductor times what? The current flowing through it. Okay. The inductance of the inductor times the current flowing through it. So all this while we've been saying that, okay, it is the current that is varying. So with the idea we have over here, or the idea we knew, we said that the inductor is what? Constant. Then if the inductor is constant, then for flux to be then the voltage that would be dropping across the inductor will be as a result of what? The change in current. Then if that's the case, if we come and find Vm, which is what? The change in the flux linkage with respect to what? With respect to time, then since this is not changing, this will become what? A constant. So we are going to have what? L, then what? Di, d what? dt. So then this is true, but not what? The entire truth. So the actual formula is that the voltage across an inductor is equal to the flux linkage dt. So then that should be what? The Li dt. Okay. Then this is the case. Now in the SR drives or in the switch reluctance module, the inductance is not fixed. The inductance depends on what? The angular position of what? The rotor, or the rotor angle. So now our L is actually equal to L of what? Theta, which is what? The rotor angle. The I is what? I'm going to call the I what? Im, like the motor current. Okay, which also varies with what? Time. Right? Okay. So then our Vm, which is the voltage, should be equal to the change in the flux linkage. So now we are going to have the L of what? Theta Im. I hope you are following. So now we have this. If we want, we can use the product rule to what? Expand this. So we have Vm. First one, we hold what? We hold this constant and we differentiate Im. So we have L theta, L of theta, the Im, the what? The T. Then we hold what? Im constant. Then we differentiate what? We find the L of what? Theta dt. Okay. So this is the expansion, but we are not done. So we are now differentiating a function which depends on another what? Variable with respect to time. Okay. So we know that if I'm finding the L of what? Theta. Okay. So I'm finding. Let me write it this way. I'm finding the L dt. Here we are just interested in finding the L dt. this is the same as what? Finding dl d theta, right, times finding d theta dt. Okay, so if we are looking for the change in inductance with respect to time, where the inductance also depends on what? The angular position, is the same as finding the change. Now we know that what? We know L is a function of what? Theta. Then if we can find what? The differential of this L, or we are able to find how L is changing with what? The position, and we are able to find how this position is also changing with time, then we can find what? The change in what? Inductance with respect to time. I don't know which scenario. Okay, so let's assume we want to find how much I want to get a scenario that you can relate with, but I'm sure you are all smart, so you understand this. But still, I want to find so we want you depend on your parents. Okay, most of us, if not all of us, most of us depend on our parents. So we are assuming that your only source of income is the amount, the stipend your parents give you. So that means the amount of money you have is a function of how much money your parents have. Okay, so we want to find how much money you have per unit time. But since the amount of money you have depends on the amount of money your parents have, then we can find the amount of money you have per the amount of money your parents have. Then we find the amount of money your parents have with respect to time. So that at the end of the day, the amount of money your parents have will cancel what? The amount of the denominator over here. Then we will still get what? The amount of money you have with respect to time. If it doesn't make sense, forget it. Yeah, so I think this equation here makes sense. So if we are able to find the change in the inductance with respect to what? Angular position, and we are able to find the change in angular position with respect to time, because with time, the rotor position here is going to be changing. Let me go back here. So with time, the rotor position, this angle is going to be changing with respect to time. And the inductance also depends on this angle. So if we find the change in inductance with respect to this angle, and we multiply it by the rate at which this angle is also changing with time, then we can find the change in what? Inductance. We can find the change in inductance with respect to what? Time. That's all I've been trying to say this far, all this while. Okay, so if this is the case, what is in physics? We saw that whenever you have a change in angular position or angular displacement with respect to time, that is equal to what? Angular what? Velocity, omega. Therefore, this equation over here, which is dl dt, can also be written as what? Dl d theta times what? Omega. I hope this is making sense. Okay, so then we can rewrite our Vm as L of theta, L of theta dim dt plus im dl d theta omega. This equation here, if you are thinking about answering question on chapter 4, you shouldn't forget this on Thursday. It's an important equation. So this is one. Okay, so this voltage here is the supply voltage. So then if I have supply voltage and I know the supply current, because we are saying if you supply this voltage Vm to the stator, remember the rotor doesn't what? Have winding, so it doesn't carry what? Current. So if we have this Vm applied to the stator and it is causing this Im to flow through the stator winding, If I want to know the power input to the motor, it's just what? Which is my input power? It's just going to be what? Vm times what? Im. That's going to be what? My input power. So then my input power should be equal to Vm, which I already know over here, times what? Im. And that's going to give me L of what? Theta times Im dim dt plus Im squared dl d theta omega. This one, I will not encourage you to chew these formulas. You see the way I've taken my time to derive them, like as they how they follow each other. So just know this: me, I don't chew formulas. When I go to examination hall and I need any of these, I'll start from the beginning. I'll prove all of them before I start answering the question. Yeah, because I can't chew these things. Yes. Okay, so this is what the input power to the motor. That's interesting. Okay, now let's look at something. We've also learned from applied electricity that the energy stored in an inductor is given as what? Half times the inductance times what? The square of the current through what? The inductor. Or the current stored in an electromagnetic material is given as what? Half times the inductance times what? The square of the current. That's interesting. So here too, this is also what? Partially true, or like 80% true. The only truth, the only reason why it's not 100% true is that here too we've assumed the inductor to be what? Constant. We've assumed that the inductor has what? A constant inductance. So then if we want to modify this a little bit to what? We want to generalize it, then this should be equal to what? Half times L of theta times what? Im squared or I squared, whatever it is. But we know that power is equal to what? Change in energy with respect to time, or what we know as what? E over what? T. Okay, change in energy with what? Respect to time. So then if I want to know the power that is stored, in the magnetic field, okay, if I want to know the power that is stored in this inductor or the magnetic field, I just need to what? Differentiate the energy with respect to time. So then that power, we call it the magnetizing power, or the power in the magnetic circuit, should be equal to what? D half L of theta Im squared d what? dt. Okay, I hope this makes sense. So then if we are differentiating this should be equal to what? Okay, so we still use what? We are still going to use the product rule. So then I hold this constant. Okay, I hold this one constant first. I differentiate what? This guy. So I'm going to have half Im squared times what? dl of theta dt plus, now I hold this guy constant. I differentiate this. If I differentiate this, I'm going to get what? The 2 will come here to multiply this, so it will cancel the half. So I'm just going to have what? L of theta. Then this is going to give me what? Im. Then after that, I have what? Dim. I'm sure you remember this from calculus, right? dt. After you bring this one down to multiply this, and this becomes Im, you are still supposed to add what? Dim dt, right? Okay. So now this is what I'm going to get. This is a magnetizing what? Or the power stored in the magnetic circuit. Okay, so I have a certain input power, and I have what? Part of this power is stored in the magnetic circuit. Then it's a motor. Okay, it's a motor. So at the end of the day, I'm looking for a certain mechanical power, and that mechanical power should be equal to the mechanical torque that is produced times what? The speed of the shaft or the rotor speed. Okay, so that means the P in should be equal to that magnetizing power plus what? The P mechanical. So that means P mechanical should be equal to the P in minus what? The one stored in the what? The magnetic circuit. So now we know P in, we know P magnetizing. So then we can determine what? Our P mechanical. So the P mechanical is going to be equal to the P in is what? Our P in is L of theta Im the Im T. So L of theta uh, L of theta Im the Im dt plus Im square dl. Okay. This guy over here, I nearly forgot. This guy over here, we know what it will result in. We know this guy here will become what? Dl d theta times what? Omega. So I'm just going to write that one over here. This guy over here, it will be it will become dl d theta omega, just like we saw over here. I think I was explaining that over here, right? D theta. Okay, so let's go on. Okay, so Im squared dl d theta omega. So Im squared dl d theta omega. Then minus the P magnetizing. So that will be equal to minus half Im squared dl d theta omega minus the second part over here is what? L of theta Im d. So L of theta um Im dim d what? dt. Okay, then clearly you can see that what this will take this guy away. Then we are left with these two guys. You can see over here that this and this are the same, just that their coefficients are different. So it's just having this everything over here is just 1 minus what? Half. Then you add whatever is here. So that means the P mechanical is just going to be what? Of Im squared, half of Im squared dl d what? Dl d theta omega. But we know power is equal to what? Torque times what? Speed. So if the mechanical power is equal to, so if the mechanical power is half Im squared dl d theta times omega, we already have omega here. It means whatever we have here is for the torque. So then the electromagnetic torque that will be produced by the machine will be what? Half Im squared dl d what? D theta. So this is the torque. Please, these two equations over here. So Thursday you should remember these two also. Okay. Even if you don't want to remember how it came about, if you want to chill these two, chill this guy too. Which guy? Okay. This guy over here. Okay. But I will not recommend that. I recommend you know how they came about. You see, we just took it one at a time. So let me stop here and take questions before we continue. If there are questions, are there questions? Please, are there questions? Okay. It seems there are no questions. So let's go on. Okay, so let me go back to the slide. Okay, so all of these have done that already. I've done this guy, I've done this guy. Okay, yeah. So then from the equation we've written, which we had the torque to be this, it means that the torque is independent of what the current. Independent of the current doesn't mean that what? It doesn't mean that it doesn't depend on the magnitude. It doesn't mean that the torque doesn't depend on the mag. It depends on the magnitude of the current, but it doesn't depend on the direction of what the current, because what the torque is what is a function of Im, and the Im over here is squared, right? So even if you reverse the current, the torque should still be in what that direction. Okay, but the torque over here depend on the rate at which the inductance is changing with respect to what rotor position. Okay, so the rotor position at any point in time affects the what the torque that is produced. Interesting. Let's go. Okay, so if the current is switched into the winding when the rotor is at a position of maximum reluctance, a torque will be what developed to pull the rotor towards a minimum reluctance position. I've already explained this. The apparent inductance of the winding will vary with what the rotor positions, which is clear from the equations we've written. This can also be approximated by the inductance profile below. Okay, so now we've seen that what the inductance of the machine, we see that the inductance of the machine changes with what? With the rotor position. Okay, so that leads us to this graph over here. Please know how to draw this graph. It's not difficult. Okay, so let's draw it.
GT,
Guys,
I can't see your screen. Oh.
you can't see my screen.
Okay, okay, that's fine. That's fine.
Okay, I'm sure your network is playing tricks on you. Okay, let's go on. Yo, nigga. Okay. Okay, so someone asked that I go over this part again. He wasn't paying attention. Okay, so we said that what so when we started from the diagram over here, we said if the rotor, so let me clean this for it to look a little bit nice. Okay, so we are saying that the rotor axis is this way. So looking at the air gap between here and between the rotor and what the stator pole over here, then between the rotor and the stator pole over here, you can see that this one has what least, this one has what or the less, it has a less reluctance or air gap, because here the amount of air gap you have is proportional to the amount of reluctance you have in your circuit. I hope that's clear. Yeah, so looking at the air gap you have here and the air gap you have here, it tells you that what this has what a less reluctance than this one. So what we are saying is that for this motor, whenever the rotor is at a position such that the reluctance is very high, the motor will what produce a torque that will move this rotor to align in such a way that there will be what a very small reluctance path for the flux to flow. Okay, then I was saying that this is just showing what just two poles. You can have like four pole, you can have six pole. So each of them at any point in time would like to have what least reluctance. So then it's possible that the time when it was here, it is having the least reluctance with a certain pole, but it's having out a maximum reluctance with what another pole. But remember that this one is switched. We said that it's a switch reluctance. So then uh, this I'm not sure, this, I'm not sure all of these stator windings are what excited at the same time. They are switched. Okay, so those of you who know how a stepper motor works, a stepper motor works is the same manner. So this is how they work. So now that this pole over here is having is enjoying least reluctance, there will be a point in time where this pole, if this pole A, this will be what? A prime. Is that okay? This is its pair. So then there will be another time where this will be turned off. This pole over here will not be excited, and this pole over these two poles will be excited. And if that happens, then least reluctance here doesn't make sense. Okay, because this is already off. So then now this is activated. So this one will also want to what? Have least reluctance. So it will cause the motor to align in this way. Then if it aligns in this way, now it has for a least reluctance. Then this one will also go off, and maybe there is some pole over here. They also come on. They also want to what? Enjoy least reluctance. So when they are also energized, they also move in that direction to have. So then you see that the motor is what? Rotating, or the rotor is what? Rotating. But these things happen very fast. You won't see it moving one at a time. Take some time to move again. No, they happen very fast. They are switched very fast. Okay, so that's just explanation of this point over here. Okay, so now we want to see how to draw this. Okay, so to draw it, you first draw these guys. This axis this way. This your what? Your inductance axis. And this is what? Your rotor angle axis. Your rotor angle axis. We have a certain maximum reluctance that will occur at a certain rotor position. A certain maximum inductance that will occur at a certain position. Now we don't know that. Then there is a certain minimum inductance that we are going to have, which will occur at a certain point, which we don't know. Okay, so what happens is that you have this. It will drop to what? It will drop to this minimum reluctance, stay constant for a certain time, then it will rise to what? The maximum reluctance again, stay constant for a certain time, drop back to what? A certain minimum, that minimum reluctance again, stay constant for some time, then rise to what? That minimum reluctance again, in this way. This is not too difficult to what? Draw. Is that okay? But the middle here, okay, the middle of this occurs at what? 90 degrees. The middle of this occurs at what? 180 degrees. Okay, the middle of this occurs at what? 270 degrees. Then the middle of this occurs at what? 360 degrees. Then this one would have completed what? One cycle. Is that okay? When the minimum occurs, when the maximum occurs, we don't know. We just know that what? The middle of this stay constant thing over here, the middle is what? 90. The middle of this place is what? 180. The middle of this is what? 270. Okay, so this looks like what? A trapezium, right? Because you can draw this like this. You can have a rectangular part here. Then you have what? A right angle triangle over here. This is like a trapezium. But later we are going to find out that the actual thing is what? The actual variation is what? Is sinusoidal in nature. But we are going to look at this before we go there. Okay, any questions so far? So that's just how to draw this here. Please know how to draw this. I won't be surprised if we are asked to draw these characteristics. Okay, know how to draw it. It's not difficult. Okay, so let's move on. So we are just to throw more light on what we've discussed so far. So we are looking at um this still what? A two pole. Okay, so at this point over here, point A, where we have what? Maximum inductance. If you know, inductance and inductance and reluctance are inversely proportional. Why? We know flux linkage, Li. That's flux linkage, right? Flux linkage. There's a certain formula like we know N Ni is equal to what? Flux times what? Reluctance. Okay, so I can make I the subject here. If I make I the subject here, it will be what? This. Okay, it will be this times S divided by what? N. Right? Okay. So if I put no, there's a formula, there's a formula. I don't remember the relation. If I put this into this, that'll give me okay. So if I that'll give me L times this, all divided by what? N should be equal to a flux linkage. Okay, so if I make L the subject, L should be equal to what? The flux linkage. I'll call it F. I'm not saying you use F to denote it. I'm just calling it F. F times what? N divided by what? Phi what? S. So you can see what? The inductance and what? Reluctance are what? Inversely proportional. So remember, inductance and reluctance are inversely what? Oh, this reluctance is S. So they are inversely proportional. It means that the point where you have the point where you have what? The least reluctance, that's where you have what? The maximum inductance. I hope this makes sense. So it is the reason why at A, look at A, at A, this is at A. Look at the reluctance you have over here. Okay, so this is when you have what? The maximum inductance. Then as you move away from the position of minimum reluctance, your what? Inductance begins to drop. So it's going to drop until a point here where it has reached what? Its minimum reluctance. Okay, so this point over here, this point B, is a point where you see it has started shifting. The rotor has started shifting. So it has started moving away from the point of what? Maximum inductance, or a point of what? Minimum reluctance. Okay, then at a point D, where this is actually what? 90 degrees, because the rotor axis is this way and the pole axis is this way. So at the point where you have 90 degrees, so here you have what? At this point you still have what? Minimum inductance. Okay, then at position 180 degrees, that is this place, you still go back to what? Maximum reluctance, because you've come back to a minimum reluctance. I hope this makes sense. Hmm? Okay, let's go on. Okay, so next slide. Okay, so now let's see how talk. So let me go back. Okay, so now we've drawn the inductance want to be like this, right? So this maximum inductance, this minimum. Okay, we said it varies this way. Okay, and this is on 90. The middle here is 180. The middle here is 270. The middle here is what? 360. So this is how the current is also going to be varying. So the current will be minimum or maybe zero until the rising phase of the inductor. Okay, so the current is going to, you have the current at its maximum between this, so here, then at the rising phase of the inductor. Okay, so the current at this point, the current is going to rise, then stay constant till what? You reach the maximum. Once you reach the maximum, the current drop by and remains like that until the next rising phase, which is this place, right? So then it goes again, then it will remain. Oh, it's taller than the first one. So then it will remain like that till what? This one reaches its maximum again. In that way, then it will what? Rise again until it reaches its maximum again. That way. Then torque is directly proportional to what? Current. So the torque is also going to follow in that same manner. Okay, so it will also be like this then. Okay, so these things are not difficult to draw. So this is a peak current. Okay, then this is a peak or torque. So this current and this was the peak torque. Okay, so now let's go into serious business. Okay, this thing. I should have done this thing earlier. But you still understand. Okay, let me see if I can copy this. How can I select and copy? Come on, let me circle this. I'm foul. I want to copy. I want to rewrite this again. I should have. So I have to rewrite this thing again. Open it again. Okay, so we said VM. We saw earlier that VM is equal to L of theta. That's the inductance with respect to the position times what? DIM. Right now, the arm goes down with it. Okay, it won't come right. So DT then plus IM DL d theta times what? Omega. Okay, this is what we got for VM. And remember, we had what? Um, the P magnetizing to be equal to what? We got L of theta times Im dim dt, then plus half Im squared dl d what? D theta omega. Okay, so I'm coming to draw this circuit. Please, that one you should know how to draw it. Okay, so this VM. This is the inductance. Okay, by the inductance is what? A function of what? Angular position. Okay, so this VM, we know Kirchhoff's voltage law. It says what? if this is a source, at the end of the day, if you take a look, the sources in the loop should be equal to what the drops in the loop, or the voltage rise should be equal to a voltage drop. Is that okay? So this is Vm. This Vm should be equal to what? The drop across this, the drop across this, and the drop across this. Is that okay? So if Vm is supplied here and Im is flowing through this, okay, that means there will be a certain drop across this. But we know the voltage drop across an inductor, VL, is what? The inductance times what? The change in current with respect to what time. But just that here, the VL should be what? L of what? L of theta, right? L of theta plus, L of theta dim d what? Dt. Because the inductance is not constant. So if that's the case, so then this is going to be L of theta, which is the inductance of this inductor over here, times the change in this current with respect to
Ima, I
time.
have a question.
Okay. Yeah, I'm listening to you.
Ima, I'm very sorry. Please, the circles, they are what again?
We've not started talking about
One is
this.
what and the other one is what?
We've not started talking about the circles yet.
But you've drawn two circles there.
Yeah, and I'm explaining the inductor before I come to the
Okay.
circles. Can we go on?
Oh, okay. Sorry. Thank you.
You're welcome.
Yes.
Okay, so we know the voltage drop across an inductor is what? The inductance times the change in current with respect to time. So here our inductance is not just what? It's not a constant inductor, or is not a constant does not have a constant inductance. So the inductance of the inductor is what changes with respect to the rotor position. And that inductance times the change in this current with respect to time will give us what the drop over here. So that means the first part of the VM has been what? Squandered. You get it? So now we are left with what? This part. This part can be written as what? Half of this plus half of this. So I'm going to have what? Half Im dl d what? Theta omega. Then this place is also what? Half Im dl d theta omega. Is that okay? So that if I'm finding Vm is just going to be what? The drop here plus the drop here plus the drop here, which will give me what? This guy over here. Let's look at something. So let's view this as what? A certain impedance. Let's view this as what? A certain impedance. Let's say a certain resistance. Then this has also a certain resistance. If I want to find the power, if I want to find the power through, or yeah, the power in this is just going to be what? The current over here times what? Times this impedance. Okay. Oh, did I say impedance? The current over here times what? The drop over here. Is that okay? If I want to find the power that's consumed in this impedance over here, it's just going to be what? The current flowing through that times what? The voltage drop across that. Or you can say that it is what? The impedance times what? The square of the current, or the resistance times the square of the current. In that case, then the resistance is just going to be what? Half dl d theta omega. Okay, here is also what? Half the dl d theta omega. Is that okay? Then let's look at something. We are saying that this is what gives rise to what? The mechanical power. Why? We saw that what the mechanical power is giving us what? The mechanical power is giving us half Im squared dl d theta omega, right? So look at this. If this current flowing through this multiplies the voltage drop here, am I not going to get mechanical power? That's going to give me the mechanical power. And we are saying that the drop, or the power consumed in this inductor and the power consumed in this guy also make up what the energy stored in the magnetizing circuits. So that will give me what P magnetizing. So look at it here. So the drop over here is what? The drop over here is just what? L of theta d Im dt. If I multiply that by the current over here, so the drop this, if I multiply by the current, that's going to give me this part of what the magnetizing power. Then if I multiply this current by this guy also, that's going to give me what the second part of what the magnetizing power. Is that okay? So then I can say that I can draw this circuit. This circuit just summarizes everything. Is that okay? This circuit over here, it summarizes everything. So it says that what this plus this guy plus this guy, they are, if you add the power that is dissipated in them, that should give you what the magnetizing power, and this guy here times this guy, the power dissipated in this guy is what gives you what the mechanical power. Please, any question?
Yes, I have a question.
Okay.
Please, brief summary. So the inductor part is what's like it's storing energy.
Yeah, it stores energy.
Then you have the two circles. One is mechanical. Okay.
Yeah, so it's
Now you have the two circles.
yeah,
One is mechanical.
yeah. So it's not only the inductor that stores the energy. We know an inductor stores energy, but this guy, we don't know if we should call it an inductor or what. But this guy also stores energy in the what, in the magnetic field. An inductor also stores energy in the magnetic field. So these two guys store energy in what, the magnetic field, or stored magnetic energy.
Sorry, my internet is lagging. When you say these two guys, you mean the inductor and one of the circles, right?
Yes, yes.
Okay.
So
Okay.
any
So
other?
the inductor is storing energy. One of the circles is storing energy.
Yes, they are storing magnetic
Oh,
energy.
Ima, I'm not done. And the last circle is like the mechanical power.
Yeah.
Okay, thank you.
Okay. So just like when we're doing the induction motors, we have one resistor that we splitted into two. We said that the one is producing what, the P slip, and the other one is producing the mechanical power. So it's just something like that.
Okay, thank you.
You're welcome. Okay, so yeah, that explains this guy. Okay, so let's look at this bad boy. So we know torque. Okay, so let me go here. We know torque is equal to T of theta. T of theta is equal to what, half Im squared dl d theta, right? We know this. So from the graph with you earlier, which we have the maximum over here, drops to the minimum, go here, whatever it is. Okay, so we can so this is changing inductance. This is changing what, rotor position. So we can find these changes. So then dl d theta is just equal to what, the change in what, inductance divided by change in what, the position, and this should be equal to what, L maximum, which, okay, so let's call this theta theta 2, and this is what, theta 1. So L maximum, okay, so these guys should be equal to what, L maximum minus L minimum, all divided by what, theta 2 minus what, theta 1. Okay, then when are we going to have the peak torque? we are going to from this one I drew here. So we have the peak torque at when we have the peak current. Is that okay? So then the peak torque is just going to be, in this case, so we are still looking at the instance where this one is changing in like the trapezoidal form. Okay, so the peak torque, we are going to see something slightly different for the sinusoidal part. So the T peak is equal to what? The T peak will be what? Half I peak squared dl d what? D theta. Okay, which is what we have over here. For you or for who? Okay, so someone asked that I go over again. So we are looking at what the change here, it is constant, so the change here is 0. But where we have inductance changing with respect to what rotor position is what is this side, this side, this side, this side, right? So the change here is going to be what? If I know the change from here up to this point, and I know the change, the corresponding change in what angle, then I can find the slope of this. So the change that we are finding here is just slope. What is the slope of this side? The slope of this side is going to be negative, and the slope of this side is going to be positive. Is that okay? So if I want to find slope, it's just a change in this, then change in this. Is that okay? So then the change in this side is just going to be what? The maximum minus or the minimum. And the change in the angle is just going to be what? Theta 2 minus your theta 1. So that's this. And we are saying that what, from the graph we have over here, from the graph we have here, we have the peak torque occurring at what? During the peak current. Is that okay? So then the peak torque will just be what? Half, we know this is a general formula for the torque. So the peak torque is going to occur at what? The peak current. So it's just what? Half of what? Instead of just Im over here, it is what? I peak squared times what? The change or the slope of the inductance position curve. Okay. Then if we know the peak torque, we like to know the mean or the average torque. So the average torque or the mean torque is given as what? If I want to find the mean of a signal, I just find what the area under the signal divided by what the period. Is that okay? So I just have to find the change in the torque from what theta 1 to what theta 2 of what the signal, which is what the torque as a function of what angular position with then the theta. Then after that I divide it by the period, which is what pi. Okay, that's going to give me the average. This formula over here also holds for the sinusoidal part. Okay, so then this over here has been found to be equal to what? The T mean has been found to be equal to what? Theta 2 minus what? Theta 1, all divided by what? The period, which is pi, times what? Theta what? Peak. Okay. Yeah, so theta 2 minus theta 1, or is it theta 1 minus theta 2? Let me confirm. Oh, yeah, it's theta 2 minus theta 1 divided by what? Pi times what? The peak torque. Okay, so if in the absence of questions, let's move to what? Okay, it's still the same thing over here. Okay, so now let's move to the sinusoidal part. We are almost done. We'll finish right now. Okay, so as I said earlier, the first the first this one we were doing. Okay, the first part we were doing, we assumed that what the change here is very sharp. Okay, so it just changes from this to this like this, then remains constant, then changes like this, then remains constant for some time, changes like this, remains constant for some time, changes like this. But it happens that what in reality the phase inductance is more likely to vary what sinusoidally rather than what as a trapezoid. Is that okay? So that means the change is more of a sinusoidal function than a trapezoidal function. Okay. So then if that's the case, the drawing is still, so you should know how to draw this guy. You should know how to draw the first one where we have it changing this way. Okay. Because depending on the question, if the question tells you that it varies sinusoidally, then you go with this guy. If otherwise, you go with the other guys. So you know the other guy with its equations, then you know this guy with its equations. This is not too much to ask for, right? Okay, so let me go back to Jamboard. So now we have it varying this way. We have it varying this way. So we still have a maximum L. We still have a minimum L. 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 So it's varying or sinusoidally. And this is the nicest sinusoidal function I've ever drawn in this school. Okay. Still, the middle, this point is what? The turning point here is what? 90 degrees. The turning point here is what? 180 degrees. The turning point here is what? 270. The turning point here is what? 360. Okay. Then the cycle repeats again. Then the current the Nyamidada now. So it will be like this during the rising phase over here. During the rising phase over here, it will go to what its maximum value. It will stay like that till what the draw when it starts dropping. So it's going to stay like this till this, then it will still go to 0. Then at the rising edge here, at the rising phase here, it will still go. Hey, it looks like one is taller than the other. Fun is that? Okay. Then it will remain like this. Then this. Okay. Then, but the torque doesn't follow this rectangular form. Okay. That one is the torque is also a sinusoidal. Oh, I don't want to draw it on another page. You nigga. Why am I disconnected? Please, can you guys hear me?
Yeah, we can.
Okay. Hey, what's happening to my Jamboard? You. Also, Jamboard, the Google said by October they are going to take it from the Google Workspace. So I'm sure it's sad and it's misbehaving. When you know you are about to die, that's what happens. It's sad. Why you didn't get it?
See, he said he left the pen at home. So let's remind him tomorrow.
So now, I'm going to use this thing now. Then after this one will stop. Yeah. Okay, so I want to draw this guy over here. So if I have the torque this way, the torque is going to be 0 when the current is 0. Okay. When the current goes to at this point where you have current, the torque is going to vary sinusoidally. So you are going to have something like this. Then it will remain 0 here. Then when this one goes to its maximum, it still what? Have something like this. So this place is going to be 90. This will be 180. This will be 270. This will be what? 360. This place is 90. This is 180. This is what? 270. This is 360. Yeah, so that's how this how the drawing looks like. Now the um let's go to the equations. So the inductance as a function of what? Angular position. For the sinusoidal one, this one is equal to a certain DC part. Okay, so L is actually equal to LDC plus what? LAC. Okay, the LDC, we are going to find the LDC is just the mean. Okay, so this is L, right? L varying with theta. It has a certain what? Average. Hey, okay.
Network.
How it's looking. Hey, Jamboard. Okay, let me refresh it. Okay. Yeah, so it has a certain average value, a certain DC value. Okay. It has a certain DC value. So that's LDC. This LDC is giving us what? The average. So LDC is equal to what? The average, which is to find the average, you find out the sum of the maximum and what? The minimum. Then divide it by 2. That's what your average, which is a DC value. Okay. Then the AC part, the LAC is equal to this guy over here, the change, which is the peak. You know, if you take an AC signal, if you take an AC signal, it is the peak times what? So if you take maybe A is equal to what? The A peak times what? Sine or cos omega or t, something like this. Okay, so it has a peak. The peak is what? Change in what? L. Then you have what? Cos 2 theta r. So this is how the AC part looks like. Let me clean this guy. Okay. Now, how do we find the peak? How do we find the peak? The peak is from what? The DC part. Oh, so from here to here, this is the peak. Right? If you want to find the peak of sinusoidal signal, is the mean position from the mean position to what? The highest point over here. So this would be what? The peak. Change in L. Okay. But how do I find change in L? I don't know this DC value. Or unless I say what the peak is what? Maybe the peak value minus the an easier way. I know L maximum, right? And I know L minimum. From here, the peak is not only from here to the top, it's also from here to what? The down. So from here to here is also what? Peak. Just that it's the peak in the maybe negative direction or in the down direction. So I know from this point, if from here to this level over here is changing L, then from here to also this level over here is changing L, then I can say that change 2 times change in L should be equal to what? L max. So because if I know this value here, I know this value here. If I subtract them, I should know from here to what? Here. So then 2 times 2 times change in L, or 2 times the peak, should be equal to what? 2 times change in 2 times the peak should be equal to what? L maximum minus L minimum. Then this should be equal to what? L maximum minus L minimum, all divided by 2. So the DC part is what? The sum divided by 2. The peak is what? The difference divided by 2. This is chewable, right? Okay, so if that's the case, we know the general torque. We know the general torque function is what? T of what? Theta should be equal to half Im squared dl d theta, right? So now we know, yeah, this torque. So now we can rewrite this guy as well. L of theta should be equal to LDC plus change in what? L cos what? 2 theta r. Is that right? So then if I'm finding dl d theta, this should be equal to the DC part to go to 0. Then if I differentiate cos, I'm going to get a negative sign. So I'm going to get negative. Then if I differentiate the angle, I'm going to get a 2. So let me just make this place theta. Let me remove the theta r. Let me just make it theta. So it's just saying the roto angle, and we know the roto angle is what we are talking about. So this will give you minus 2 change in L sine 2 theta, right? So then the torque equation will now be equal to what? The torque equation will now be equal to what? Half times Im squared times minus 2 change in L, or just 2 times change in L, okay, sine 2 theta. These 2 over here will cancel these 2 over here. So then your torque function just reduces to what? Im squared change in what? L sine 2 theta. Then if you have a sine function like this, what is its peak? Your T peak, the peak value is just what is in front of the sine. So that will be equal, the T peak will be equal to what? Im squared change in what? L. Compared to the other one, which was what? Half I peak times what? dl d theta. Okay, so now for this side, what you need to remember is how to find change in L, which is L max minus L min divided by 2. How to find LDC is what? L max plus L min divided by 2. How to find change in what? How to find this bad boy? Okay, you need to know this as well. Then you need to, the rest you can do. I won't ask you, I won't expect you to chill it. I expect you to what? Know how to derive it, like how I took my time to derive everything. So then now we know the T peak. What will be the T mean? The T mean will be what? It's just 1 divided by pi as usual. The differential from what? Pi on 2 to what? Pi. Okay, so just from here, from what? This is 90, so that's pi on 2 to what? Pi. Okay, to pi Te of what? Theta, the what? The theta. And you know T of theta to be what? This guy over here. I hope this makes sense. Yeah, so basically we've almost come to the end of the course, the chapter. Yeah, so everything is here. Everything is here. Okay, so control of switch reluctance drives. So there are two basic modes of operation for the hot. There are two modes of operation for the switch reluctance drives motor. The mode in which you are going to operate it depends on what? Its speed at that particular time. And the aim of all this mode of control It's just to what? Control the current, because if you control current, we are controlling torque.
Oh,
Then,
Emma, I have a quick question.
okay.
Emma, please, what is the limit pi on 2 and pi?
Hmm?
The limit of the integral function.
Why is it? Why is it
Can you
from?
hear me?
Yeah, I can hear you. Why is it
Why
from?
is at the limit pi over 2 and pi?
Yeah, so we are finding the average.
Yes.
We are finding the average torque over here. Okay. So the average torque over here. So the area that will be the area under this. Okay. So from we are taking from yeah. So okay. So do you agree that the cycle ends over here and
Okay, I
begins
think I
over
get
here?
it. So like 90 and 1 day.
Yeah, I'm saying when you are
Yeah, I
finding
get.
when you are finding average, what do? You find you find the area, right? You
You
divide it by what? You find the area, you divide
by the
it
period.
by the period. Okay. So do you believe that the cycle ends here
Yeah.
and the new cycle begins here?
Yeah, I get it now.
Okay. So your question is
Yeah,
answered.
yes. Yes, thank you.
You're welcome. Okay, so um yeah. So we said there are two basic modes of operation that we can control. Okay. And the mode that you use, or the mode depends on what? The speed of the rotor speed at any point in time. Please, if you have any question, please ask. Oh, Thursday is not too far. Where am I? Okay, then uh both modes aim to control what? The current in the winding, because to control torque you need to control current. Okay, and even to control speed, to change speed you require what? A certain amount of force, because to change speed is to what? To accelerate. And if you need to accelerate, you need what? A certain force, because from Newton's law, F is equal to what? Ma. That means in order to accelerate you need a certain what? Force. So the first law says what? A body in motion will continue to be what? Like if a body is moving at 2 kilometers per hour, it will continue to be moving at 2 kilometers per hour. That means it will be in equilibrium at 2 kilometers per hour until it is acted upon by a certain force, external force. And if that force acts on it, it's going to cause it to what? Accelerate. And the rate of change in momentum is proportional to what? The force that acts on it. That brings about this equation. Okay. So then, if you want to change speed in a motor, in a way, it is what? A certain torque. You need torque to change speed. Is that okay? You need torque to change speed as well. And to change torque, you need to what? Control the current in the winding. In the winding here there is no what? Rotor winding. So any winding we are talking about here is the stator winding. Is that okay? So because current directly controls the torque in the machine. Then the first mode is that we said the mode depend on what? The speed, right? So then the first one is at low speed. At low speed, the aim is to control what? The current amplitude in the winding during the period of what? Increasing what? Inductance. The mode of the point where we have inductance increasing, that is from here to here, or the other one from here to here. During this phase, I think this wasn't drawn well. Yeah, so during this phase, this is where you have what? Inductance increasing. At this point where you have inductance increasing, that's where what? You see that's when you have your maximum current. Okay, so if you want to control torque, then you should be able to what? Control the amplitude of this current. Here you are not what? You are not perturbed, or you are not worried about the mean current here. You are worried about what? The maximum current here, because the maximum current here determines what? The maximum peak that you have. Is that okay? Even in the sinusoidal one, the maximum, where you have the maximum torque, you have the maximum torque occurring at what? The maximum speed. Is that okay? So in a way, even over here, yeah, the peak current still what determines your maximum torque. So if you want to control torque, then you should be during the low speed when, so if you are operating at low speed and you are at what the rising side of the inductance and position curve, your aim is to what control the peak peak. Okay, your aim is to what control the peak. If you control the peak current over here, you control what the maximum torque or the peak torque. Is that okay? Then at high speed, so oh god, knowledge is sweet. Yeah, so at high speed, the aim is to what maximize the mean what current. Why? Let's go back to this thing we drew over here. Can I submit to you that okay? Can I submit to you that this over here is your back EMF? Because we have VM, which is the supplied voltage, to be equal to what this guy over here. So just view this as when we're doing the DC motors, you have a certain supply over here, which is V, right? And you have a certain resistance over here. Then you have what? The motor back EMF. So this is this place. So this place is actually the back EMF. Okay. So we know that back EMF EB is proportional to our speed. And you can see that
Alex, so my internet is lagging. Which place? Can you say where your mouth?
yeah. The cycles.
Here where? Like, can you
The
describe?
cycles, the cycles.
Okay.
Okay.
Okay, thank you.
So this is what happens at low speed. It means at low speed, your this one is what? The lower the speed, the lower your back EMF. That means the lower this side. Okay. And if the lower this side, then the higher the current that will be flowing. Do you see that? Because at the end of the day, VM is equal to, let me reduce this size more because it's too big. Because at the end of the day, this is what I am L. Let me just write it as L. DIM, the what? DT. Then plus what? If you add these two, it will be what? IM omega DL the what? The theta. So if the back EMF is very small, let's assume that the rate of change here is constant. The rate of the slope is constant. Okay, so if the slope is constant, if the speed is low here, it means this back EMF here is low, which is this side is low. If it is low, that means the difference between this side and this side is going to be what? High. Higher compared to when this speed is high. If that's the case, then the current over here has to be what? Very high. Is that okay? So that means at low speed, your current is very high. But as the speed increases, this value over here will start what? Increasing because it is proportional to what? Speed. So as the speed increases, the current will be reducing. Okay, so here you are just interested in what? The mean torque. Is that okay? You are interested in the mean torque that will be produced. So at high speed, the aim is to what? Maximize what? The mean current, because the mean current controls what? The mean torque, or determines the mean torque. So maximize the mean current during the period of what? Rising inductance, which is achieved by what? Timing of the position and the width of the current pulse. The current pulse in the sense that you see the current is what? Pulsing. So it comes high, it stays that for some time, then it goes low again, then for some time it comes. So the current is what? It's a pulse, because what? The motor is what? It's switched. So it's like you are sending pulses. So those of you who are working with uh, Arduino stepper motors in your project, what is actually sent to the motor is what? A pulse. So that pulse, one of the pulses will go, uh, uh, one of the pulse will go and go and energize a certain phase. That will cause the motor to what, move through a certain angle called a step angle. Then another pulse will go. Is that okay? But sometimes it goes so fast that you see the motor is just rotating. So those who are working with, you see sometimes the motor will just move clean, then it will stop, then it will move, then it will move, it will move. Yes, because it's what, you have current pulses what being sent. So you talk about the pulse rate and all that. Okay. Yep. What am I supposed to say? It's like I'm over talking. Yeah. So if you want to control the mean current, to determine the mean current, the mean current over here will be what? The area under this. Okay. So that means if you are controlling the width, okay, the width of the pulse is just here. Okay. So you've heard about pulse width modulation. In pulse width modulation, all that you do is what? Uh, you modulate the width of this pulse. Is that okay? Because modulating the width of this pulse determines, also modulate what, the signal you are modulating. Is that okay? Then the timing, which is the frequency also what affects the mean pulse. Okay, some of them were taught in power electronics. Okay, so I think I've already explained this. At low speeds, the current builds up very quickly in the winding when a voltage is applied. This is mainly because the back EMF term is what, low. So the phase current must therefore be what, controlled by what, chopping. So because the current magnitude at low speed, the current magnitude is going to be very high. You want to what, reduce it so that it doesn't. So it's like you are setting a certain boundary. That okay, this should be what, the boundary. So if the current is rising and it reaches that value, it has to what, chop. Is that okay? So you have something like this. So it means the current can't go beyond this. So if it gets here, it's what, the current is what, chopped. Is that okay? So if the current is chopped, then the torque is also going to be what, chopped, because the current affects the torque. Okay, and this happens during what? It's only during the rising phase that we have current flow. We have the current pulse. Is that okay? So don't ask. So what will happen during this phase? That side, the current is zero. Okay. The rest you can read. These ones you can read them. I'm not sure you are preparing for exams. Okay. Okay. So let's solve the examples. We should stop. Let's just finish this one. So chapter 4 will be in 1 minute. This one takes 2 questions. Okay. So the first question says the inductance rotor angle characteristics of a single phase switched reluctance motor with 2 stator and 2 rotor poles is shown below. Okay. So this is it. This one you'll be given the characteristics. If you are not giving characteristics, you should be able to draw this. Okay. So I'm going to draw this before I read the rest of the question. So I have this over here. From my spirit to my soul, all to my miracles, you are worthy of my worship. So this L max, then this L minimum, L min. Okay, then from the question, this place is what? The reduction starts from what? 15 degrees. Then it ends at what? 75 degrees. Then always I tell you that what, the middle of this place is what, 90 degrees. Okay, we don't know this yet. The middle of this is what, 180 degrees. Now let's read the rest of the question. It says a motor drive A motor drives a large inertial load and may be assumed to rotate at what? A constant speed. Okay, we got it. When the rotor is at an angle beta, where beta is between what? 90 and what? 105. Let me go and write down that condition. So a certain angle beta, which is between what? 90 and 105. Okay, so I have that. So okay, right now I don't want to indicate where beta is. Let's maintain composure and read. Okay, so when the rotor is at an angle beta, a constant voltage of 135 is applied to the motor. So at that angle beta, that is when the voltage is what? Applied to the motor winding, which may be assumed to have what? The motor winding may be assumed to have what? Negligible what? Resistance. Okay. The current rises to what? 10 amps at theta equal to what? 105. Okay. So then safely I can come and say that this point over here is what? 105, because it's during the rising phase of the inductor that you have what? That you have the current rising to its maximum value. Okay. So the current rises to 10 amps at theta equal to 105 and remains constant at this value for what? Theta between 105 and 165. Then I know that when the currents rise to its maximum, from all the characteristics we've drawn so far, I know when it rises to its maximum, it will be at its maximum until it reaches what? The maximum inductance. So then if the current is going to be constant until what? 165, it means it's going to reach what? Its maximum inductance at what? 165. So 165. Is that okay? So draw an equivalent circuit for the motor winding and hence determine the following. This question here, that draw an equivalent circuit for the motor winding, is not asking you to come and draw this guy or what? The sinusoidal one. It's asking you to draw what? This guy. So this is for this for the circuit. So this is kind of the equivalent circuit. So this is Vm, and there's what? Im flowing here, and there's what? L of what? Theta over here. This guy is Im, half Im dl d theta omega. The thing, as you work with it, like it will even stick. You don't have to chew it. So Im dl d theta omega. So I've answered the first question. The next question says what? Hence determine the speed of the rotor speed. Okay, this is interesting. So as you see the first one, then you start asking yourself, okay, where do I go from here? I've been given this Vm. So first of all, let me write something. So I have Vm is equal to what? L of what? Theta times what? Im, right? Oh, no, there's no Im here. That's what is the power that has the Im. So just what? Dim dt plus Im dl d theta omega. Okay, so I've got you. So I'm supposed to find the speed of this motor. Now let's look at something. So let me go back to the question. Okay, so the speed of the rotor the torque producing during this region. So we are finding the speed of the motor. Okay, then what do we have to do next? Do we know L of theta? No, we don't know L of theta. We have dim dt. We know the maximum current, which is 10. Okay, so that means this place we know this. We are coming to determine this. Okay, let's look at something. You see, during this phase, the current is not changing. Do you agree with that? During during this phase, okay, during this phase, the current doesn't change. Does it make sense? It runs at constant speed, so it means here it's running at that speed, here it's running at that speed, it's running at that speed. But during here, current doesn't change. Okay, maybe let me draw the current, this one for you, so that you can visualize it. So it's going to be like this until it reaches this point before it rises. Then you have the maximum. Then it's gonna be like this. Then here. Okay, so during this side over here, current doesn't change. Even during here, current doesn't change. Do you get it? So the beta we will look for later. The beta is between 90 and 105. So beta is somewhere here. So it is around this place that the voltage was applied, which is 135. Okay, so that means during here there's still 135 applied, but what current doesn't change over here. So if current doesn't change over there, it means what dim dt is 0. So then dim dt is equal to 0. Then if that's the case, if dim dt is equal to 0, then Vm should be equal to what? Dim dt equals 0. So Vm should be equal to just Im dl d what? Theta. But we know dl d theta is equal to what? L max minus what? L mean divided by what? Theta 2 minus what? Theta 1. You remember? Good. Okay, yeah, there's supposed to be omega here. Okay, so then this should be equal to what? What's the maximum? The maximum is what? 0.1. 0.1. The minimum is what? 0.01. All divided by what? Theta 2 minus theta 1. That's 75. Or you can use 165, depending on which edge you are using. So 75 minus 15. If you leave it this way, you better with it. You get it? So if you leave it, it means this is in degrees, but what? You are going to find the speed in what? Radians per second. So you need to convert this angle over here to radians per second. We know that what? 2 pi is equal to what? 60. 2 pi equal to 360, or pi equal to 180. So then what should be? This will give you 60. So 60 pi should be what? Less. If less, more divide. Right? So you are going to have 60 divided by what? 360 times what? 2 pi. So then this will give you what? This will give you 180. Okay, so this is going to give you what? 60 times what? Pi on 180. So just take it. Anytime you are converting from degrees to radians, you multiply the degrees angle by what? Pi on 180. Then anytime you are changing from rad to what? Degrees, you multiply by what? 180 on pi. Okay. Okay, so then I'm going to multiply this by pi and multiply the numerator here by what? 180. I hope you understand. Yeah, so what will be the L d theta? The L d theta will be equal to what? Calculator board. So it's 0.08 what 59. Eh, what's in the slide? 9 59. Okay, 594. Okay, we will just use 4 decimal places. So okay, so this is it. Okay, so if that's the case, we know this guy, we know this guy, we know this guy. So we are going to have 135 is equal to 10 times 0.0859 omega. So then omega should be equal to what? Omega should be what? Is it 135 divided by this, or this is divided by 135? Okay, so what should that give us? So 135 divided by 10 times 0.0859. That will be what? 157.16. 1557.16. And this is in what? Radians per what? Second. So if you multiply this by 60 on 2 pi, that will give you in RPM. So this we are getting 157.16 rad per second. In RPM is what? 1500 RPM, right? Yeah, so that's for the speed. The next question is to find what? The torque. There are two ways you can find the torque here. You can find the mechanical speed. After that, you can find the mechanical power. After that, you divide it by this speed you have here, or you find the torque directly. Me, I want soft life, so I'll find torque directly. So if you want to find mechanical torque, you just do what? P mech is equal to half Im squared dl d what? D theta times what? Omega. That will give you the mechanical what? Power. But I know if I just take half of this, if I take I say half, if I take this part of this, that will give me the torque directly. So why should I waste time and go and find this after that? Come and divide it by this W again. So soft life gang, we move. So I'll just find torque directly. Yo, Chairman is frozen again or what? So half Im squared dl d what? D theta. So this should give me what? Half times what? 10 squared times 0.08 0.0859, and that should give me what? 4.295 Newton what? Meters. 95. Hmm? No. Now, it will have units. It will be this one. Inductance is Henry's per rad. Okay, so that's the talk. So we are done solving the first two. Now we need to find what? The angle B. So angle B, let's go back to the diagram we have here. So in this diagram, B is occurring here because we know this place is what? It started rising at 105. And we were told that what? Beta is between what? 90 and 105. So that means beta is somewhere here. So we are still going to use the Vm equation, this Vm equation here. So Vm is still equal to what? L of what? Theta dim dt plus Im d theta, dl d theta omega. Okay, now let's observe something. So we have IM over here, we have the IM over here, and we have the T on here. We have DL, the theta over here. But look carefully. During this phase, can you see that the inductance is constant? During B, at B, the inductance is what? Constant, because the inductance is equal to what? L mean. Is that okay? So between 90 and 105, the inductance is constant. And if the inductance is constant, it means that what? dl d theta is equal to 0 at that point. Or the slope there is what? 0. So if the slope there is 0, then Vm reduces to what? Hey. Then Vm reduces to just L of theta. L of theta dim dt. But there's no need for us writing L of theta again, because L is what? Constant there. So since L is constant, then we are back to our favorite formula. That's L di dt. So dim dt. Okay, I have dim dt, but there's no way I can directly find im dt based on the this one given to us. So I can rewrite this as, so this the same as writing dim d what? Dim d theta, or yeah, dim d theta times what? Times d theta dt, right? I know how during this side, during here, I know how currents changed. So during this constant, I know how currents change with respect to what? With respect to what angle? Okay, I know the current change from here to from 0 to what? 10. But I don't know how the currents change with respect to time. So that's the reason why we are doing that. So then I have this. Oh, I'm not supposed to be here. So then this over here is what? This over here is what? Omega. So then I can say Vm should be equal to L dim d theta omega. I know this guy. I know this guy. I know this guy over here, which is the im. That will be what? 10 minus 0. Is that okay? So then I can say that Vm, which is 135, divided by what? The speed, which is 157 point. We are 157 point something. 157.16 rad per second. So rad, where are you? So 16. Then here times L. L is what? From the question, L is what? L mean is 0.01. This should be equal to what? 10 divided by what? Change in what? Theta. Is that okay? So then what is what would this give you?
85.18. 85.18.
Divide that by 10. So 0.1. What did you do? You found the answer straight away. Okay. Okay, so yeah, if you do this, change in theta should be equal to 0.116. So 0.116 rad. Okay, if you want to get it in degrees, we multiply this by what? 180 on pi. So this should be equal to what? 6.67. So 6.67 degrees. Okay, so this change in theta we've gotten here is what? Okay. No. Is what? The change from beta to 105. So you see, that's when we have the current changing to this. So we are looking at what's the change from here to here. That is what we got as what theta, change in theta, and we are using the corresponding change in what current. Is that okay? So then, if we know from here to here, and we know this the final value here, if we want to come here, we just subtract the change from what the final value, and that will give you what the initial value. So then it's just going to be what 105 minus 6.67, and that will give us 98 point what 98.33 degrees. Yeah, that's for that question. Circle. We. Okay, let's solve the last question. I'm tired. Okay. So the second and the last question. It says that when the phase inductance of an SR motor, thus it has two stator and two rotor poles, was measured, it was found to vary sinusoidally. So this one says what it was the inductance was found to what change was sinusoidally with what rotor position. So me, the moment I read up to this point, I see this vary sinusoidally. Now, in my question paper, I'm going to draw, or my answer booklet, I'm just going to draw this. Yeah, yarrow now, yarrow. Okay. So then, this will be the inductance part. So I have my maximum over here. Nah, maybe. Then I know the current. So this place is what 90. I know the current is going to behave this way. Then at this point, then like this. Then I'm tired. Okay. Then I know the torque is also going to vary. So this current, I. Then I draw a torque. So then this one, but this one will be what sinusoidal in nature. Then sinusoidal is, yeah. Once I draw this cry, if I don't answer the rest, I'll get some marks. Yami order. Yes. So yeah. So me, I've gotten to this part of the question. I've already if I draw and I'm not able to solve, you will see that I will understand the concept. It's just that I'm fat. Yes. So various sinusoidal with rotor position, and to have maximum and minimum values of what 50 millihenries and 10 millihenries respectively. So I go back to my darling over here. This is what 15 millihenries. Then this place is what 10 milli what henries. And the moment I see this that varies sinusoidally, because I don't want to give the enemy the chance, I'm going to write my LDC formula there so that in case I finish drawing, I don't forget. So I'll go and write what L max plus what L mean all divided by 2. Haha, I've written it down. I write on my change in L to be what L maximum minus L minimum all divided by what 2. The devil is alive. So I write T of theta to be equal to what half Im squared dl d theta. Then I come and write my T mean is equal to 1 on pi from theta on 2 to from pi on 2 to pi this. So if you see such question, you are able to write all these, and you are not able to solve that one, like your own be spiritual. You get it? Because now you have all the armor you need to solve this question. You get it? So yeah. So the first question says, sketch a graph of what phase inductance versus rotor position for this machine. I've already answered that question. So that is this part, right? So maybe you drew this on your question paper. So you just take your answer booklet and just put this one over there nicely. Like, look how nice it is, as if like I just drew it in MATLAB. That's nice. Yeah. So I've answered that question already. Then the next question says what? Assuming a suitable control circuit and an ideal variable current source are available to provide what? Up to 10 amps for what? Phase energization. Okay, so that means that's telling me that what? When my current shoots, that's the maximum current it goes to. So yeah, I come here. I said, okay, this guy over here is what? 10 amps. Right? Life is not supposed to be difficult every day. Then, and neglecting the effect of resistance and magnetic saturation, draw the current and torque characteristics versus rotor angle for this machine for for the machine for operation at a maximum motoring torque. And okay, so now it says I should draw the torque and the current characteristics with respect to what? Rotor angle. I've already done that, which is this guy and this guy. Oh, God is good. Yeah, remember this place is also on 90 or pi on 2. This is on pi. You see, if you write 90 and like uh, those who are not engineers or those who don't know much, that they will see that oh, this is not anything. But if you write pi, somebody will now be thinking, what is pi? Yeah, so like to make it more technical, let's use pi. Pi on 2 and pi. Yes, we are technical people. So pi. This is 3 pi on 2. And this is what 2 pi. Yes. So just like the this one we did today, like we don't use break, we use what? We don't use open, we use break, we use make and things. Yes. Oh, this is also recorded. Yes. I forgot we are recording. Okay. So the next question is for us to find what? The peak torque. Then after finding the peak torque, we are also supposed to determine what? The mean full load or torque. Okay. So then let's go and finish this hard. Some few minutes more, you can go and have your dinner. This economy, you guys still have dinner. Hey. Okay, so LDC will be equal to what? 15 millihenries times plus what? 10 millihenries, all divided by 2. And that should give me what? 12 milliwatt henries. Hey, 12.5. Hey, master teacher. So 12.5 millihenries. Then 15 minus 10 all divided by 2, that should give me what? 2.5 milliwatt henries. I'm solving it. Okay, so what should be my dl d theta? Okay, let me write what dl is in the first place. Oh, let's move to red. Any brava? Hey, red, you saw it. Let me refresh. Please, can you guys hear me?
Yeah, we
Yes.
can.
Okay. Let me move to red. Like, any brava? Okay, so L. I like red. Yeah, I'm a butcher boy. Yeah, so L of theta will be what? LDC plus what? Change in L. Plus change in L, then what? We have cos 2 theta, right? So that means my dl d theta should be equal to what? Minus 2 change in L sine 2 theta. So then I can now substitute the value into this. So I'm going to get minus 2 times change in L is what? 2.5 millihenry. So that's 0.0025. Then what? Sine 2 theta. So this will give us what? 0.05, right? So this will be 0.05, 0.005, right? Sine 2 theta. Okay, I know my talk, this one looks like this, right? So if I come here and substitute this, I'm going to get what? Okay, let's do, so if we substitute that into this, we are going to get what? Half, we know this half im squared times what? This times this, that's minus 2 change in what? L sine 2 theta. So this will cancel this. So I shouldn't have even multiplied. So this will give me minus im squared change in what? L sine what? 2 theta. Okay, so this one I shouldn't have. So then our TE of theta should be equal to minus im squared. So that will be minus 10 squared. Change in what? L, that's going to be times 0.0025. Then what? Sine 2 theta. So what will this give us? Hmm? So we get negative 0.25. See 0.25 sine what? 2 theta. So then our peak torque, T peak, should be equal to what? 0.25 Newton meter. Please, is it clear? Etasa and Antase. Hey, you mind me? Or you are still processing?
Ina, could you go to the
Processing.
previous slide? I want to see something.
Yeah.
The previous one, the one before this. Uh-huh. Okay.
Metum to us. Can I go on? Please, can I go on?
Yeah.
You guys are eating, so you don't want to mind me.
Yes, you can go.
Okay, so the next thing is for us to find what the T mean. So the T mean is equal to 1 on pi. The integral from what? Pi on 2 to pi. TE of what? Theta. Theta, d what? D theta. Okay. Why I can't, hey, why, John, what if you get to 20, you can't add some again? Go for your class for. But we so we they do things sometimes. Have they taken it? Hey.
Ajite, please have a question.
Okay. Ajumia. Yeah, please, you can ask.
Please, how did negative 0.25 become the other thing at the bottom there?
Which other thing?
Can you open
Yeah, I've
can you
opened it.
open the can you go back to where you were?
Yeah, I'm there. Maybe your
I
this one
can't.
is lagging. Right,
Okay, I see.
which
Yeah,
part
I'm
of
I'm here
KNSC
too.
are you at?
So how the TP where did it come from?
So if you have a sine function,
Pardon?
if you have a sinusoidal function in this way, what is the peak value?
0.2. Ah, okay, thank you.
Okay, sure. We move. Okay, so now let's find a T mean. So T mean. Oh, now which color should I use? Hmm? White. Okay, I'm going to use white. So if you can't see, it's because I'm using white. So I'm actually writing. Okay, let's change the background. Life is sweet. Okay, so let's write with white. Yeah. Oh, we should change the background again. Yeah, let's finish. I become hungry. So, yes. Okay, so T mean is equal to what? Pi on 2 to pi. Te of what? Theta. D theta. So this is equal to, wait, there's 1 on pi here. So 1 on pi, integral from what? Pi on 2 to what? Pi. Then we have a, oh, this guy. Okay, so we have 0.25 sine 2 theta. Okay, so 0.25 sine 2 theta. So 0.25 sine 2 theta the what? The theta. If we integrate this, what are it's minus, right? So let's bring the minus outside. So we are going, this should be equal to minus 0.25 divided by what? Pi. Then we integrate what? Pi from pi on 2 to pi sine 2 what? Theta, the theta. Okay, so if you integrate sine it to give you a negative cos. So this place is 2. So this is going to give us minus 0.25 on what? Pi. Then this place is going to give us what? Minus cos 2 theta, all divided by what? 2. You know, when you are differentiating, you multiply by this one. If you are integrating, you divide. So pi on 2, then what? You have what? Pi. Right, so if you put the limit into it, you have minus 0.25 divided by what? Pi. Then you are going to have, so if you bring these 2 over here, you are going to get 2 pi here, right? Then this place is going to give you minus cos pi. Okay, this is 2 pi, so minus cos 2 pi minus cos. I could have just swapped the limit and ignored the negative, but let's go through it. So then this will give me a minus cos pi. Okay, so then this is going to be equal to what? Minus 0.25 divided by what? 2 pi times cos 2 pi, that's what? Cos 360. Cos 360 is what? And cos 360 is 1. So minus, that will give you minus 1. Then cos pi, which is cos 180, is minus 1. Minus 1. No, cos pi is what? Yeah, cos pi is negative 1. Then minus 1, that will give you a minus. Okay, so this minus cos pi, that will be minus 1. So that will give you 1. So this will give you minus 1 over here. So then this should be equal to, so you get minus 2 over here. This minus 2, the minus here will cancel the 1 here. Then you are going to have a 0.25 divided by what? 2 pi times what? 2. Then this will cancel this. So at the end of the day, your mean torque is just what? 0.25 divided by what? Pi. And that is what? 0.0796 Newton what? Meters. So yeah, that's the answer. Thank you. End of chapter 4. Hooray! Clap for yourself. Okay, there is one question in chapter 3 I want to solve. I solved it in the first video, but I've had a lot of people asking me that like the thing is confusing and things. So I want to solve it again, addressing the issues you guys had. Where is it, girl? It's in chapter 3. Yeah. Yeah, this question. So, okay. So the question is, the per phase equivalent circuit of a 4-pole 415 volts 50 hertz induction motor may be approximated to a magnetizing inductance of 60 millihenries, a rotor resistance of what? 0.453 ohms. The rated speed okay, so the rotor resistance of, oh, if you guys are okay, we can just skip this. For me, I'm tired. Should we solve it?
Yeah, solve it.
Okay. So the induction motor may be approximated to this. The rated speed of the machine is what? 1480 RPM. Calculate the rated output power, the rated torque, and the rated current. So let's go to jump. Oh, why have you changed the background? Okay, so it says it can be what? Approximated to a magnetizing inductance of 600 millihenries. So then a rotor resistance of 0. So we have this over here. Whatever it is. We have this over this 600 millihenries. So that's 0.6 henries. Then the rotor resistance is what? 0.453 ohms. 0.453 ohms. Okay, so the rated speed is what? 1480. So then we can determine the slip. Is that okay? So it says what? It's a it's a 4-pole machine. That means the number of pole pair is what? 2. So then our synchronous speed should be equal to 60 times what? The frequency is 50 divided by pole pair 2, and this will give us 1500 RPM. Therefore, our slip S should be what? 1500 minus 1480 divided by what? 2. Hey, divided by synchronous speed, that's 1500. So this would be what? 1500 minus 1480 divided by 1500. So the slip is 0.013 what? 33. Okay, so this is our slip. And if you remember, what are we finding? Calculate the rated output power. Okay, so that's the mechanical power. We know that there is two parts of, if you take the rotor resistance, which is what? R on what? RR on what? S. We have two parts. One part produces what? The mechanical power, and the other part produces what? The P slip, or the slip power. Okay. So we said that what? The part that produces the slip power is what? Is R. And the part that produces the mechanical power is what? R on what? 1 minus S divided by what? S. I don't know if that's right. Okay, let's expand this and see. Yeah. That will give you this. Okay, so to get a mechanical power is the motor current that is flowing times what? The motor current that is flowing times what? Squared times the resistance. So P meg will be what? IR squared times what? R 1 minus S divided by what? S. You see, these things you don't have to chew them. You just have to know the principles. Okay. So now IR has not been given. So I need to determine that. I know IR is given by what? The voltage V1 divided by what? Okay, since we are ignoring the inductance of the rotor, it's just V1 on what? RR on what? S. That's IR. So then if I put this into this equation, oh, background. So then I have P mechanical to be equal to what? What am I going to get? Okay, so I can determine IR. So let's just do that. So IR, since I think that's also a question here. So IR will be equal to what? V1. But V1 is the per phase voltage. So that would be what? 415 divided by what? Root 3. And that will give you 240. So that will give me 240 divided by the resistance, which is 0.453 divided by what? The slip, and we found the slip to be 0.0133. So 0.0133, and that will be equal to what? So we'll get to 7.04 what? So 6. Okay, so that is what the rated what? The rated okay, this is not the rated, this is the rated rotor current. So now we come here. What will be the voltage here is what? The voltage here is 240, right? So now we've determined this current. The rated current is the current flowing here. Okay, so we need to determine the current passing here, which is what? IM. So IM is going to be 240 divided by what? The impedance over there. The impedance there is given as what? 2 pi times what? 50 times 0.6. So 240 divided by 2 pi times 50 times what? 0.6. That, what are we going to get? 1 point. This is equal to 1.27 what? 3 amps. Okay, so that means the rated current, which is what? IS, is equal to what? the phasor sum. So we are going to get 1.273 squared plus 7.046 squared, and that will give us what 7.16, just 16. Okay, so 7.16 amps, which is the answer you have over here. Kajiko, yai. So the next one is to find out the power. So to get the power, now we know IR to be this. We've already written what? This one. So P make. These people, I'll see them. I want black. I'm black. I want black. So P make is equal to IR squared, which is 7.046 squared, times R, which is 0.453, all divided by what? All divided by 0.0133. Then this place times what? 1 minus S. So 1 minus 0.0133. So we close this. So what is P make? Remember, the power here is per phase. The P make here is per phase. So that will be equal to what? So whatever answer we get, that 1668.46 watts. Multiply that by 3, that will give you the total mechanical power. So the total mechanical power is this times 3. Hey, what am I saying? So if you do that, you are going to get 5.0 5.01 kilowatts. Okay, so my torque TE is going to be what? The mechanical power, which is 5.01 times 10 to the power 3, times what? The speed, the rated speed, which is 1480. This is in RPM, so I multiply this by what? 2 pi, and I multiply the torque by what? 60. This will give us what? The torque. So the torque, what are we getting? 32.33. So 32.33 Newton watt meters. Okay, so this is what the torque, the rated torque. So now the question goes ahead to say that now let's move on to the next part of our problem. Okay, we are moving. The induction machine we've been working on fits a load which can be characterized by what? This equation, TL equal to 5 plus. So this is the main reason why I'm solving all this question again. So TL equal to 5 plus 0.05 times what? Omega R, where omega R is the mechanical speed in what? Rad per second. Calculate the speed and torque developed when the stator voltage is reduced to what? 380. So initially we have what? 415. Now we are reducing it to what? 380. We are reducing the voltage to 380. Is that okay? So then I'm just going to solve for the 380. You use that same method to solve for the 250. Okay. While still at what? A frequency of 50 hertz. Kajiko. Yay. Okay. So what is confusing a lot of people is that when they solve and they go back and look at the solution inside here, they found the speed and they are now doing some pole pair thing, and they said, but this speed is already in mechanical speed because of what is here. So why are we converting to mechanical speed? Okay, so in solving this question, we know that torque. So in order for the motor to drive this load, it must generate what? An electromechanical torque. That would be equivalent, that should be at least equivalent to what? This load torque. Is that okay? So then, so we know the electromechanical torque generated in the motor, the induction motor, is given as 3v1 squared times pole pair times resistance, resistance times I think S omega E, yeah, divided by uh, omega E, omega E squared R squared. Or let me go back and go and check what I have. I don't remember. I have to prove it all over again. That's okay. Let me go and check the formula again. Okay, so that's if you ignore this. Okay. So let me see what that is going to give me. Okay, 3p v1 squared r on top here. I have SWE on. Okay. Okay, so let me derive that sharp. So I have 3v1 squared p r, right, divided by S omega E times r squared divided by S squared. So this should be equal to 3v1 squared times p times what, this r, all divided by this will cancel this. So I'm going to have WE r squared on S. If I send this S up, I'm going to get 3v1 squared p times r times S, all divided by omega E r, right? So if I put WE over here and I square this, it's the same. So then I can confidently say, okay, so this place is squared. Sorry. So this place is squared. So this r here is going to cancel the square here. So I can say that, okay, so then what I wrote here is correct. Okay, so if we have this, so this will cancel this over here. So I can say TE should be equal to a 3v1 squared times P times what, SWE, right? Then all of this divided by omega E squared times what, R. Okay, so this electromagnetic torque should be equal to what, the TL. And so this S times so WE is equal to, so this S times W, I can rewrite this as what, TE equal to 3v1 squared times P. S times WE, remember it is what, omega E minus what, omega what, R, right? So then this should be times what, omega E minus omega R. Okay, it has understand, so you don't have to leave people thinking too much. So omega E minus omega R all over omega E is equal to what, slip. So then if you multiply this by this, that will give you this. Okay. So then if I have this all divided by what, omega E squared times R should be equal to what, TL, which is equal to 0.5 plus 0.05, right? 0.05 omega R. So then people are saying that, so why are we still converting it to mechanical speed? The issue is that the omega r here and the omega r here are not the same. They are similar. This is what? They are all rotor speed, so they are all similar. But this is what? In mechanical speed, and this is in what? Electrical speed. Okay. And we know there's a relation between mechanical speed and electrical speed. Is that okay? So to make this understandable, there are a lot of ways you can go about it. One way is that I'm going to do the conversion straight away. Since electrical speed is equal to pole pair times mechanical speed, is that okay? Times the mechanical speed, let me call it omega m. So when people see omega r here, they see omega r here and say, oh, it's the same thing. So then the answer we got is the mechanical speed. No. It ain't. You got it? Yes. So you could say that, okay, since electrical speed is equal to electrical speed omega e, let me not call it omega e because we know omega e, we are using omega e here as synchronous speed. So omega r is equal to what? P omega what? M, which is the mechanical speed. Then one way you can do it, okay, if that's the case, then come and put in place of omega r over here, come and put what? P omega m over here. Then with that, the answer you will get straight away will be what? The speed in what? It will be the mechanical speed in rad per second. Another way you could do it is that instead of writing omega r here, you replace omega r here by what? Omega r on P. With that, so with that, the speed you get will be what? Electrical. Then after that, you still what? No. One way, the first way is that you come and replace this by P omega hot M. So now we are changing this to omega M. Is that okay? We are not using omega R. So now this is omega M. So then the answer you get will be in what? Mechanical, will be the mechanical speed straight away in radians per second. Or you come and do what? You come and replace omega m here by what? Omega r on P. Then the answer you get will be what? Electrical speed. So you still have to come and convert it to what? Mechanical speed. Is that okay? So it's because they all have omega r. That's what making it confusing. In the solution in the slide, the assumption made is that let the omega r we have over here be the equivalent of what? This omega r, so that you have omega r, but you have it at the back of your mind or your skull that they are not what? The same. Okay, but that can be what? Very tricky, because especially in examination settings, like you've gotten your answer, you are so happy. Eboa. Okay, so okay, let me use one method. When I finish and I still have energy, I'll do the first one. So now for the load torque equation, we are replacing the omega r by what? Omega m. And we know that what? Omega r is equal to what? P omega m. So now in the electromagnetic torque equation, we are going to replace omega r over here, which is the electrical speed, by what? Its equivalent mechanical one, which will be what? P omega m. Is that okay? So now let's do that and solve. So now we are going to have TE to be equal to 3V1 squared times what? P times omega E minus P omega M, all divided by what? Omega E squared R. This should be equal to what? TL, which is equal to 0.5 plus 0.05 omega what? M. So the speed we are going to get here straight away will be what? The mechanical speed. So now we can solve. So now our V1 is no more 240. It's going to be what? 380 divided by what? Root 3, because our line to line voltage has changed. What's the phase equivalent? 380 divided by root 2. Root 3.
219.
So that's 219. So then we are going to have 3 times 219 squared times what? The pole pair. The pole pair is what? 2. Times the synchronous speed, which is what? 2 pi times what? 50 minus 2 times what? Omega m, record up, divided by what? 2 pi times 50 squared, right? 2 pi times 50 squared times what? The resistance, which is 0.453. This should be equal to what? 5 plus 0.05 omega m. So what will this part give you? 3 times 219 squared times 2, all divided by this. What have you done? I want just this part. I want this. Is this my calculator? So that's what. So this part over here is going to give you what? 6.436 times what? 100 pi minus 2 omega m should be equal to what? 5 plus 0.05 omega m. Then this times 100 pi will give us what?
This 5 times 100.
2022. 2022. What happened in 2022? 05.05 minus this one will give us what? 12.872, right? Omega m should be equal to a 5 plus 0.05 omega what? M. So now if we bring this bad boy here and we send this bad girl here, we are going to have a 2022.05 minus 5 should be equal to 0.05 omega m plus 12.872. Yeah, these two, this minus this will give us, this will be 20, 0, then we get what? 17, right? 0.05. This place should be 17. Okay, that should be equal to this plus this will give us what? 12.87 plus 0.05. So there's 2 over here. Omega m is what? 12.92. 922 omega m. So what will be omega m? 2017.05. 2017 was when we went to SHS. You had a 156. 156.09. So this should be the mechanical speed. So rad per second. Let's go to this one, the solutions we have here, and let's see. Which question is this? Is this the question we are looking for? Yeah. Where is it? What did they get? Okay, so you don't multiply by this 310.99. What will you get? Or you to let's convert our own to let's convert ours to RPM so that they will see. So multiply what we got by 60 on 2 part. So if you do it, we get out 1490 point what? 0.59 RPM. Yeah. So okay. No, I think we left something somewhere. There's okay. I think I multiplied that 1490, and here they had out 1485. There's the difference is too huge. 5 difference. It shouldn't be that. These are decimal places. The difference is too huge. Let me check. So 3 times this times this. Okay, so I'm just confirming. Nah, it's not in this book.
Yeah, you can solve it.